So this is an example question from the chapter 9 in Baldi and Murray that we're going to go over real quick. So it's based on the principle that there are like continuous sample spaces, and we plot those density curves and find the area under the curve to get those particularly probabilities, because finding ultimately the area under this density curve, that area represents the probability. That's our ultimate vision for upcoming chapters that will help us in statistically testing association between two variables. So let's just for this chapter understand the probabilities given the probability of under the area, under the curve, or the area for that particular. Here we don't have the curve, but it could be in different forms you can think of. So let's go over this. Let y be continuous random variable with uniform distribution. We compute various probabilities, and this is the graph given to us. So we can say that okay, there is margin of 0 from 0 to 0 0.5, 0 0.8 to 8, so total probability is 1, right? So we can see that these are like the total this is the total probability. So if we are looking at probability of 0 or y being greater than 0 but less than or equal to 0.5, so y being less than or equal to 0 from here to y being less than or equal to 0.5. So that is the actual area of interest. That will be the probability of that thing. And in this case, the area is given as 0.5, so that's why answer is 0.5. Similarly, you can see that even if it is y greater than 0 and less than 0.5 and not equal on either of these ends, the probability still remains same. Why? Because probability of only one point, either 0 or 0.5, they simply doesn't have any value, so that's 0. So we can see that probability of y being 0.5, if you want to calculate, that will be 0 because that doesn't represent any area under any kind of graphical presentation, most commonly used as density curves. Then similarly, we can also think that probability of y greater than or equal to 0 but less than 0.5, it's also same 0.5. So these are some basic principles to look at before calculating area under the curve. So probability of y less than or equal to 0.5, so everything below 0.5, you know the lowest probability will be 0, so you know that will be till 0, so that will be the same again. And then probability of y greater than 0.5, so you know total probability is still 1, so everything greater than 0.8 to 1, that will be probability of y being greater than 0.8, and that particular area is given here as 0.2, that's my answer is 0.2. Now if we want to look at probability of y less than or equal to 0.5, so that particular region, or probability of y greater than 0.8, that one. So whenever we have this or, we use addition of these two probability for as a multiplication rule, as a addition rule, right? So what do you think that will be? That will be probability of y less than or equal to 0.5 plus probability of y greater than 0.8. So this probability plus this probability, we know this is 0.5 and 0.2, right? But sometimes but we have to know that whether these events are independent, these are disjoint event or non-disjoint event, because as a general rule we just do probability of A or B equals to probability of A plus probability of B because it's R, and we subtract the interaction of two events, probability of A and B, right? if the A and B looks like this. That's the general rule. But we can say that if this is our A event and this is our B event, there is simply no overlap between these two events, right? And that's why we can say that these are having no joint, so these are disjoint events, so you're going to just simply add this probability. So let's move on to this another question. What is the probability that randomly selected female has heart rate less than 110? So heart rate is less than 110, and we want to calculate what is the probability. So probability is area under the curve, and particularly less than this particular 110 milestone. So everything before that, and you can cross check that whether these are density curve or not by adding these probabilities, so that we can know that all of these constitute to 1. So this is less than 25, so approximately 25%, 25%, 50. This is, I don't know, maybe 85. This is 590, somewhat around 10%, so about 100%. So we know that this is probability 1 total. So we know this is, we are dealing with density curves. That's the another way that we can confirm, so that we can decide whether to apply the probability rules if required or not. But this is just a simple question. They are asking us probability that randomly selected female has heart rate, and that's the female data, so we don't have to worry about the male or female thing, um, less than 110. So we have to just find area below 110. That will be this area and that particular area, right? So we say that that will be 0.35 approximately, and this will be 0.23 maybe, and then you just add them together, because if you want the heart rate less than that, that will be this or this anywhere, so you just add those as addition rule. So you can think of that as probability getting heart rate between 100 to 110, or probability getting heart rate between 90 to 100. And since these are all, you're going to add them, and that will give you answer about 0.58 somewhere. So that will be answers. Let's look at this last question. 8% of patient waited at least how many minutes? So this also based on probability principle, and if you can read through this question 10 and look at this graphical presentation. Some data is given to you in terms of time, so that's your variable, and this is the area given to you, curve, and area under that curve given to you. And again, you can cross verify by adding this number and see, but and out of that we have to find 8% of the patient waited for at least how many minutes. So we have to find the corresponding x value, or that variable value in this case. So 8%, if you try to look at this first area under the curve, that represented as 0.2, that's nothing but 2%. If you further go, that will add up to 0.2 plus 0.6 as 0.8, right? So that is the area of interest, right? And when we say at least 8%, 8% of people waited at least how many minutes? So that's the corresponding x value, so 20 minutes, and that's why the answer in here is 20 minutes. But it's not the typical question, but it is just giving you the practical implication of this probability principle, how it is useful in finding the area under the curve, and in later chapter we are going to actually find these area p-values and in statistically testing the associations. So in this particular question from chapter 10, textbook Baldi and Murray, this particular question asks us to calculate some probability based on this data. So let's read through this. So it's regarding birth control pills that have theoretical annual efficacy of 99.5 and real world efficacy of this. If college student takes a pill for 4 years, she is in college, what is the probability? That's the question. What is the probability that she will become pregnant at least once out of 4 years using the theoretical efficacy rate? So basically we have to use this theoretical efficacy rate so we can simply forget this other information. So we know that this is the probability of theoretical efficacy of oral contraceptive pills or birth control pills is 99.5% or 0.99 in other words, right? But what is that probability? Is it the probability that randomly drawn person or that female will become pregnant for particular year, or is it the probability that she will not become pregnant? So that's related to the theory behind this. So oral contraceptive pills, basically these are for prevention of birth, basically birth control pills. So basically to avoid the pregnancy. So your pregnancy, your efficacy, so your pill will be effective. That means you will or someone will not get pregnant, right? So probability in this case is equal to probability of not getting pregnant. So that's the thing, right? 0.995. And we want to consider it for 4 years. So if we are considering 4 year, at least among these four become at least once pregnant at least once. So think about the sample space that will be for 4 years. Maybe in all 4 years she will become pregnant. That's one probability. Or she will become pregnant only on first, not pregnant on second year, not on third, not on fourth year, and you can think of other possible events. And then there will be this possibility as well that will she will not become pregnant on any of these 4 years. And there could also be several combination of these according to sequence, but the point here is to elaborate like the total possibility. Out of the total possibility, there will be only one time or one event that will say that she will not become pregnant in any of the 4 years. Our question is asking probability that she will become pregnant at least once. So that means, okay, here she is getting pregnant at least once, actually four, once, twice, so at least one. So these fulfill. But here she's not getting pregnant at least once. So all the 4 years not pregnant. So we know that we have to exclude only this particular event out of all the possible event from the total sample space. That is total probability is 1. So we have to subtract that from probability of not getting pregnant and on all these years. That will be your probability of becoming pregnant at least once in 4 years, right? So you can also write it as probability of becoming non-pregnant on first year and probability of not becoming pregnant on second year and so on. And since we are using it and we have to use the multiplication rule, so that will be probability of n for the first. And we have to consider, we have to assume here that in all the 4 years the probability remains same over a period of time. So that's the assumption we are making. So that's why we are saying that these are going to be the independent events, and that's why we are going to simply multiply those events a times b, not the conditional ones. So that's nothing but n raised to power 4. So that's the fourth power. We know that probability of not getting pregnant is given as 0.995 by theoretical efficacy. So you just solve that part mathematically, and then you should be able to get something like this. So your final answer will be 0.0199 or about 2%. So you can also think and solve the other problem using the other probability as a practice.